Hello all and welcome. I hope you all enjoyed last video of motivation behind studying numerical method. We at Walaita Sodo University are happy to have you with us. As we discussed earlier, as engineers, you would encounter a necessity to model physical phenomena and the real-world problems such as heat transfer, regulation, and control. In order to solve those, engineers often have to employ simplifying complex models that use numerical methods. The first concept engineers should master in the process is linear algebra. So, linear algebra encompasses topics such as foundation, system of algebraic equation, and method of solution. Whether the equation be linear or nonlinear. Throughout, an explanation of those topics will be presented with subsequent expression and mathematical formulae. Of course, the discussion will be reinforced with contextual explanations followed by numerical solved examples. This is vital to deepen your understanding, so stay tuned. Let's start with basic concepts. Taylor series helps to approximate complex models in your pursuits of finding numerical solutions for aforementioned problems in your frequent engineering career encounters. So Taylor series is an expression of any functions in the form of continuous sum of terms, such as evaluation of function about a point of evaluation A, followed by consistent product of subsequent derivative of consecutive order, and the segment which is x minus a divided by the factorial of the n, which is the order of which derivatives are computed. These are often used in transforming an engineering models, often involving complex functions, as we stated in the introduction, to the simpler, manageable polynomial form functions. Such approach is vital particularly in computer model development corresponding to engineering variables such as CFD and automation of regulation and control. This is because numbers or numerics are the only thing computers and systems understand. Computer and the control systems have no clues about what language you speak or your subtle engineering design, but numbers. Therefore, everything should be provided to those systems in numerical entries. That's why we should study this course. Maclaurin series, on the other hand, is typical Taylor series evaluated to the point 0, where a is equal 0. These concepts and their essence will be made clear to you with graphical illustration. Once again, you will benefit a lot if you bring us your complete attention. Suppose we are to convert a function e raised to x using Taylor expansion. As we all might know, the derivatives of any order for the function e raised to the power x is itself e raised to x. Having this, we can evaluate e raised to x near x is equals to 0 using Taylor series. Remember that Maclaurin series is a special Taylor expansion about Taylor evaluation point 0, where a is equal to 0. To simplify, put it, Maclaurin series is Taylor expansion when a is equals to 0. So let's proceed. Derivatives of e to the power x is itself. Recall Taylor is evaluation of function about a, in this case 0, which is Maclaurin. So e raised to 0 is 1, which is the first term in the Maclaurin series. Similarly, the second term is Taylor expansion. In the Taylor expansion is the first derivative of e raised to power 0 times 0, which is 0, because we are evaluating Taylor expansion about the point 0. Pardon me for using Taylor and the Maclaurin series interchangeably. The same is true for the third term, where the second derivative of the function e raised to 0 evaluated at is 1, multiplied by x minus 0 square is x square divided by 2 factorial. Next, the fourth term is the third derivative at 0, which is 1, multiplied by e minus 0 cubed, which is x cubed, divided by 3 factorial. Therefore, the Taylor expansion of e raised to x evaluated at 0 is 1 plus x squared to 2 factorial plus x cubed divided to 3 factorial. If you compute this with the given evaluation point where x is 0.1, it results in 1 plus 0.1 squared to 2 factorial 2 plus 2 factorial is 2 plus 0.2 to 3 factorial, which is 6. When you compute this, the result will be this. Use your calculator to evaluate e raised to the power 0.1. The exact value is like this. You could see the result nearly the same, where error is minimal. In fact, your calculator actually engineered to use these steps to evaluate your entry. E raised to the power 0.1. Did you get how important is this? The same is true for almost all your digital or computer control device. Thank you. Next concept is intermediate value theorem. So it is an evaluation of existence of a root between a given range. You see, engineering involves finding solution to an equation. Suppose you are given an equation to solve. When you evaluate the function at a and b in this range, if the product of f at a and f at b is negative, meaning the value of f at a or b is negative, the intermediate value theorem states that there should be it should cross the line where f is equals to 0. In this case, f is 0 when x is at the point 3. This is only true given the function is continuous. This is essential in determination of solution for the function within a given range. Of course, techniques in engineering is way advanced than this topic, but without understanding this, those might confuse you. So this is basic. I think you can try examples given in the lecture note provided. Now, let's conclude this part by seeing how accurate is Taylor evaluated at different points. Let's take cosine function as an example. As you can see, the thin smooth lines colored in red, blue, and black corresponds to the functions which are analytic. Cosine of x plus 2, and cosine of x minus 3 respectively. Now consistently colored marked short broken plots represent corresponding Taylor expansion, which is numerical. First at x equals to 0, these Taylor expansion are evaluated dropping all subsequent terms from the third term onwards. For example, look at the black smooth mark of Taylor approximation about a is equals to -3, and then notice how it is closely approximate the cosine function cos x minus 3. Similarly, notice the same trend for Maclaurin, which is a special Taylor expansion for cos x, as well as cos x plus 2, where the values of a are -3 and 2 respectively. You can take your time to read through the remaining examples and the contextual explanations. In the reader I provided for more, and for these are a bit elementary. You frequently encounter those topics in solving system of linear and non-linear equations, defining integral and differential equations, aka tensorial calculus, and ordinary and partial differential equations, i.e. ODE and the PDEs. And that of course will be the last topic in numerical method, which is ordinary and partial differential equations. Studying these, you will employ these concepts for engineering analysis. Now, let's advance to a bit advanced topics or concepts which I perceive the most challenging chapter of this subject, but at the same time the most exciting. We engineers consider system of linear or nonlinear algebraic equations and the techniques used to solve them elementarily. Although they might seem elementary, their applications in engineering put them ahead of everything else, which I noticed throughout my over a decade of my engineering career as an academician. Indeed, linear algebraic equations are a system of m linear equations in n unknowns, 1, 2, up to m rows of equations, which x1, x2, up to xn unknowns. The linear algebraic equations can be compactly written as capital A times x equals to b, where capital A is a matrix of row m, which corresponds to the number of equations you would encounter in modeling engineering variables such as heat or energy, mass or continuity, and fluid force or momentum, whereas n corresponds to a number of variables, let's say temperature, pressure, velocity, and so on, their counts. N also corresponds to number of columns in coefficient matrix, capital A. x1 up to xn are, as I told you, the variables themselves. Therefore, n can be constant multiplier for every variable, say thermal conductivity or any other material property in your model. So this capital A times x equals to b is called system of linear algebraic equations. We will discuss their characteristics and method to solve them. Mathematicians provided us with important characteristics of matrix form in eigenvalues and eigenvectors. So these terminologies are vital parameters for us engineers in analysis system. Whether you opt to determine structural stability, such as vibration and the dynamic response through computing natural frequencies and the mode shapes, or thermal stability analysis such as temperature gradient decay and heat distribution patterns. So within a linear algebra, recall the equation capital A times x equals b, the concept of eigenvalues and eigenvectors take following form. Let A be any square matrix of order n. Then there exists lambda such that for any scalar lambda, the following condition of transformed equation in matrix form can be satisfied. By the way, recall a square matrix is a matrix of equal number of columns and rows. Capital A minus lambda times A, I, the whole in the bracket times the variable array x equals to 0. Here is a new terms introduced in the Eigen theorem. I is the nth order identity matrix. Notice the consistently similar to the number of variables and columns, or columns in our linear algebraic equations. Lambda are eigenvalues of given matrix A. Unlike x's in linear algebra, the vector x here in eigenvalue equation is called eigenvector of corresponding eigenvalues, which is characteristic variable. So why should we bother about eigenvalues value theorems after all? This example is taken from a website description of heating up. The citation is given in the document for more. So consider heating up time, whether you model your oven or anything. This equation is also known as lumped thermal system modeled by differential equation. The total derivative of temperature with respect to time, aka transient temperature variation, equals the product of coefficient matrix and the nodal vectors plus source heat. Thus capital A is equation 5 can represent thermal conductivity, convective heat transfer coefficient, and discretization scheme in a real-time model. Now finding eigenvalues lambda and the eigenvectors v's of coefficient matrix A leads to analyze the stability and the transient response. So that condition AV equals lambda V to be satisfied. Now suppose the following spatial temperature distribution A given. If you want to determine stable gradient decay, or the process involves calculating eigenvalues, and the same process, which is true for spatial heat distribution determination, that involves using eigenvectors, you should determine those characteristic equations and values of Eigen theorem. So capital A minus lambda times I, the whole in the bracket times variable array x equals to 0. So since capital A is given, determining eigenvalues, eigenvectors and eigenvalues offers insights to us about temperature distribution and the thermal stability of the system, respectively. As you may recall from your undergrad mathematics class, solving above equation follows determining the determinants of coefficient matrix. Since this is 2 by 2 matrix, you can easily calculate the difference of the product cross multiplying corresponding entries in the matrix. Capital A minus lambda times I matrix. Remember, I matrix is 1 0 and 0 1. Recall matrix multiplication and the steps in the equation seen. This results in characteristic eigenvalue equation of form lambda square plus 9 times lambda plus 18 equals 0. The value of lambda negative with a couple of vectors or arrays corresponding to each lambdas. The first real part vector 1 vector 1 v1 positive implies stable thermal mode. You may also see examples in the reader. Thank you.